We're at the last lesson. We're supposed to have 2 weeks for special relativity, and we keep losing lessons. We've done time dilation, we've done length contraction, we did the mass energy equivalence, and that tricky equation, which isn't in the syllabus, but I would expect you to be able to use it. The kinetic energy, gamma minus 1 m naught c squared. The last phenomena that occurs with objects traveling at relativistic speeds is relativistic relative velocities. Okay? Now let's consider the old school example of someone on a skateboard that throws a baseball. All right? Classical mechanics says that you would add the two velocities up. And somebody standing off to the side would see the baseball as v plus u prime. We'll add some terms in a moment, but you could just combine them. So this obviously doesn't work. Let's consider this example here. If I said v, try again, let's go u equals v plus u prime, that's going to be 0.6c. The spaceship seems to be travelling at 60% the speed of light, and it fires a missile 0.7c, and so you would see it as 1.3c. Well, that breaks the rules. We cannot see any object in a different frame of reference to be travelling faster than c. Okay? So I've just added here, u prime is always going to be the velocity of an object with respect to v. Okay, so he's measuring v, and then he's going to look at that missile, and he wants to know what u is. So u prime is always going to be the speed from the moving reference frame, okay, or from the other frame of reference. Okay, so obviously the classical mechanics says that it is not going to be 1.3. What we need is the Lorentz factor. It's been tweaked a little bit, and we have two equations that appear in our data sheet, but it basically it brings that velocity back to below the speed of light. It prevents us from breaking the rules. Now, I've added this recently to the booklet. I did this the other day. Obviously, you have this booklet printed. There is a calculus derivation. Doc Physics, who we've seen a couple of his videos, does a crazy large derivation. Obviously, it's in the link up here. There is a derivation if you want to, if you're a masochist and you want to follow his mathematics and his rearranging and his algebra, you can, but we don't need to worry about the derivation, okay? He also does a couple of very quick videos. They're like 3-minute videos that shows a scenario. We're going to do similar scenarios in today's lesson. Okay. There also is another derivation. Again, my stamp, the not in syllabus stamp. You do not have to worry about how it was derived, but you have this equation in the data sheet. Now, what you will first notice is that the numerator is the classical addition of v plus u prime. So the speed of the spaceship, add the speed of the missile relative to the spaceship, you combine them together. But underneath, here is it looks similar to the Lorentz factor. We've got v times u prime divided by c squared. Now, this is a really cool equation that will always divide such that the denominator is larger than the numerator. So if we said if the numerator was 1.3c, boom, it's going to be divided by a value bigger than that. It brings our speed back to under 1c. So let's take this equation and we'll put it into application. Come on, laptop. I'm waiting. Thank you. Let's put that into this scenario. Okay, so here we go. U equals v plus u prime over 1 plus v u prime over c squared. Now, it looks nasty, but if you leave things in terms of c, it becomes a very simple fraction. Look what happens. We get 0.6c plus 0.7c over 1 plus 0.6c, 0.7c over c squared, and we can cancel out the c terms, at least in the denominator, the c terms cancel. Let's just simplify it again. We get our classical relativistic speed, but then look what happens. 1 plus 0.6 by 0.7. Now, you guys are good at maths. 0.6 and that's 0.42. 1 plus 0.42 is 1.42. Oh, look at that. We've now divided our large number by a larger number that gives it brings it back down. We get 0.92c. So that is what this person would see the missile travelling at. Okay? So again, we cannot ever see an object travelling faster than the speed of light. And gentlemen, I hope you are writing nice things. Don't write anything nasty on my wife's birthday card, or else I will have to rip it apart. All right? I don't want her bursting into tears because of my nasty year 12. And I do appreciate you helping me out here by giving her a nice birthday present. We might frame it, put it on the wall. Okay. Now, we could go in different directions. In this, we were stationary and it was travelling right, travelling light. Right. No, not travelling light. Travelling right. Positive values. Brendan, Robert, pay attention once you've finished. We need a sign convention if we're moving left and right, backwards and forwards. So over the page, let's just consider that we fired it backwards. All right, look at this one. Now, I've already done the working out for you, but what we're going to add here is please assign a convention that one way is positive, the other way is negative. Okay? And you can see that's why we've got that there. So now, when this bloke observes the missile, here's the thing. He sees the spaceship travelling past at 0.6c. The spaceship fires a rocket backwards from its frame of reference, U prime. It's measured to travel backwards from the rocket at 0.3. Now again, when combining these values, we're not going over the speed limit. But it's not just v plus u prime. It's not going to be 0.3 because these are both relativistic speeds. And long story short, there is time dilation and length contraction occurring in these reference frames that we have to consider. So the answer is not just 0.3c right. We have to then add the Lorentz factor that does all of the hard work for us. Okay? But look what happens now. With the sign convention down here, we get a negative fraction, which is then going to be 1 subtract 0.18. So now we're dividing it by 0.82. So it's strange to think that we would actually see the missile travelling travelling away from us a little bit faster than if it was just a skateboard throwing a baseball backwards. It's actually travelling away from us faster. So this is combining the relativistic effects of the spaceship moving and the relative effect of the missile moving. Okay? Now, we've got some space here, and I wanted to fill it with an example. Oh, here was an example. Let's go back to, please, the first page, page 40. Okay? Even at slower speeds, we still need to factor this in. So let's consider, in a different coloured pen, what if I said u prime was 0.1c and v was 0.1c? Remember we said 10%, that's when we've got to start figuring stuff out. And so I just want to quickly show you again, we'll use the same equation. So obviously we're going to get 0.2c on top, but now 0.1 times 0.1, I think, look what's happened. That's now going to become significant. It becomes 0.2c over 0.99, which does in fact change the speed that we observe it at.
Wait a minute.
Oh, sorry, my bad. I can't talk and do maths at the same time. 0.2 divided by 1.01, 0.198, sorry. Okay? So, okay, when we're adding relative velocities, there's probably going to be some lower limit, Cameron Garside, that we don't have to worry about it. But you will be given these thought experiments. Consider a spaceship travelling at this speed and a missile at this speed. It's not going to be lower. Okay? And sometimes this does occur. You can have particles travelling that might decay and spit out an alpha particle or a beta particle that's travelling at relativistic speeds. So it does occur in nature that you have to observe one particle from a frame of reference that is not the particle, if that makes sense. Let's continue on with an example. Okay, it gets tricky. I need you, if you have 3 different pens, I'd like you to now consider 3 different pens. Okay? Red, blue, and 3 different coloured pens. Okay? So, now let's make things a bit tricky. Okay? Consider 2 spacecrafts, both travelling at 0.8c and moving apart from each other, and you're smack bang in the middle, the stationary observer. Okay? In this case, here's what we could do. Set U as one rocket ship relative to the other, and V to the stationary observer. That would be travelling away from the rocket ship. What does this all mean? Let's try and put it down. I'm going to say, let's go from this guy's frame of reference. He's going to be observing U with a speed V. So you become the imaginary spaceship. Okay? And then, because the blue spaceship on the left was measured relative to the stationary observer, he becomes the imaginary missile, which is U prime. Then, we could measure U. Okay? So what I've done here, I'm going to use the same equation in your data sheet, which is U equals V plus U prime. Let's try that again. V plus U prime over 1 plus V U prime on C squared. But what I've done is I've done a bit of a transform. I've said, let's now transform to be in the frame of reference of the bloke in the right spaceship. Okay? In which case, he sees this imaginary spaceship, the stick figure, travelling that way at negative 0.8c. So now our V becomes negative 0.8c. And then this blue spaceship was measured from him, so he now becomes the missile that was fired from the imaginary spaceship, the stick figure. And so U prime is always relative to this guy that's in the different frame of reference from who we want. It gets a little bit tricky, but let's write it in, negative 0.8c. So, I'll just do, this is from the stick figure's frame of reference. Let's quickly solve. Oh, I put a negative down there because I've assigned that right is positive and left is negative. So let's throw everything in. Negative 0.8c plus negative 0.8c over, got to keep my negatives, okay. Now all the c's squareds cancel. Let's rewrite this. The classical addition would be negative 1.6c. Of course, that is not the case. Look what happens in the fraction in the denominator. We get negative 0.8 by negative 0.8 is positive 0.64. And if we add a positive 0.64 to a 1, oh look, we've got a value that's larger than the numerator. We get negative 1.6 over positive 1.64, and we get negative 0.976c. The negative is because I assigned left as negative. So from the green stick figure in the right spaceship, he observes the left spaceship to be travelling left at 0.976c, not the 1.6 that would break the rules. Yes?
So if you're determining like a relative velocity, does the denominator have to change? Because if one's negative and one's positive, the denominator will be less than 1, which will make the numerator. And in the eventual speed grade?
Let me try and give you an example where we can use the other equation in your data sheet. Oh, that's lovely. The other equation in your data sheet, I don't even remember because I tend to use this one. So let me just quickly bring up the other equation in the data sheet. And I'll draw it, let's go in red. The other equation is u prime equals u take v over 1 minus vu on c squared. Now, you can, it's a bit tricky, but you can rearrange one equation to get the other. So if I'd asked you to rearrange u prime to get u prime on its own, I'd have to sit down and have a long think about it. You would be able to rearrange from one to the other, but you don't need to. They're both in the diagram. They're both in the data sheet. But here's what we could do. You could say, well, I'm going to observe this bloke to be u, this bloke to be, now hang on, make sure I get this right. Two space.
No, so the one going left has to be u.
U and V.
Yeah.
V is the other one. And then u prime should hopefully be, no, that's not going to work because you're going to get, oh yeah, no, it'll work. And then that would be u prime. Now remember, u prime is always the speed with respect to the v. Yeah? So, remember, the speed of him relative to him. So I'm thinking we're going to get a negative. I'm thinking we're going to get a negative value. Now, using this, v is going to be plus 0.8c. U is going to be negative 0.8c. All right, can you see what we've got here? Different frames of reference, different directions, different signs. Okay? Now, I don't want to confuse you by showing you both methods. Because in the third example, I'm going to put ourselves in the other spaceship. But anyway, let's just do this middle example with the u prime equation. So here we go. U prime equals negative 0.8c take positive 0.8c. Oh, that's nice because then we get a negative 1.6. 1 minus v is going to be 0.8c. Oh, a negative 0.8c over c squared. Let me get my cancely. What's happening underneath? Let's rewrite it. Negative 1.6c over 1 minus 0.64 is positive 0.64. So we get a double negative. And we get minus 0.976c. Okay? Lastly, let's use a lovely blue coloured pen. I'm going to put a blue person in a blue spaceship. Either method is perfectly acceptable. This one just requires you to do a bit of a shift and go, well, I'm going to see from perspective of the right. Let's now go, this guy here. Let's go from this dude in the left spaceship. Okay? In which case, he measures V of the imaginary spaceship, which is the person, to be... You see I've got reds and blacks and blues all over the place now, so hopefully it doesn't get confusing. I'll just write V there. And then he is firing the imaginary missile, which is U prime, and then he wants to observe U, the speed. So it's like saying, from the perspective of the dude in the left spaceship, what speed is the right spaceship travelling away from him? Okay. Now for this... Over here we started, on the right side everything was travelling left, and so we had negatives and negatives. On the left side everything's travelling right, so we're going to be dealing with positive land. Basically, we're going to get almost the same as that fraction, but there's going to be no negative signs in it. And we're going to end up with exactly the same value, or magnitude. So I'll just quickly write here V equals plus 0.8c. U prime is also plus 0.8c. U equals question mark. Well, it's going to equal V plus U prime over 1 plus V U prime over C squared. Cancel, cancel, cancel. 1.6c over 1.64, you get a positive 0.976c. So that's pretty good. This guy reckons, and the classical relativity would agree with this. The bloke on the left reckons the bloke on the right's moving right at 0.976, and the bloke on the right reckons the bloke on the left's moving left at 0.976. And the bloke in the middle goes 0.8, but never 1.6. Yeah? Now, do try it yourself. Oh, why have I got such a large black block of paper there? Let's have a look here. I want you guys to have a crack at this question. Let's just scribble in what's going on. Here's the Earth. And we've got two spaceships. Now, I'm just going to go, let's go, the first spaceship is traveling this way. Enterprise. So here's my Enterprise, or let's just go capital E, or let's go ENT. And then we've got another spaceship going this way, and this is the Discovery. Okay? Relative to Earth and relative to Earth. So we've got V Enterprise equals 0.7c, V Discovery is 0.85c. Okay? Well, the answer is, the answer are those values. So this is a silly question. It's given in the question, relative to Earth. The answer is right there. From someone on Discovery, they go, okay, right, Earth says that Discovery's moving 0.85 left. Discovery goes, no, Earth's moving 0.85 right. All right, that's just your equal and opposite. There's no confusion there. But now we've got to do relativistic velocity addition down here. An occupant of the Enterprise says Discovery was, let's find the velocity of Discovery relative to Enterprise. Now, I'm going to slice this down the middle. In one, we're going to use the U prime equation, and in the other, we're going to do a bit of a shift and pretend that you're a stationary observer in the other. So, we want Enterprise. We want U prime from V. And this guy is the U. Okay? Because we're saying the people on the Enterprise are saying the stuff. So we've got to say, well, they're now they're moving relative to Earth, and then they're trying to look at U prime, which is their view of the fired missile. So, in the black text, I will give you the U prime. In your data sheet, it says U take V over 1 minus VU on C squared. And you'll solve that for me in just a moment. But I want you to also, let's put a green bloke in the Enterprise. I don't know where I'm going to do this. Let's put a green bloke in the Enterprise, and then the Earth becomes the imaginary spaceship, which we measure as U. No, we don't. We measure it as V. And then the Discovery becomes the imaginary bullet fired by the imaginary missile, and then we want to find V. No, we want to find U. Okay? So, I would like you to do both. But be careful. We need a convention that right is positive and left is negative. I'll give you a hint. You're going to get exactly the same answer and exactly the same direction, but you've got to flip some values in both scenarios. Okay, so give it a go. And also remember, you're expecting a value less than C. So if you stuff up or get the wrong direction, then you can sort of gives you a hint that you've made a mistake somewhere. Wait, have I stuffed this up? I've stuffed this up. I've stuffed this up. V is positive. And look at that. Hopefully, if you're up to that stage, the denominator is now bigger than the classical addition. It's bigger than 1.55, and that's going to drag our number down to negative 0.972C. Okay. Again, negative because I assigned left as negative. So the people on the Enterprise view the ship travelling left at 97.2% the speed of light. Okay? Who was able to get that without copying me? Am I giving you enough time? I don't want to... There's no point me doing it all and you copy it down and give yourselves a go first, and I'll play catch up.
I've given it a crack challenges. In the second equation, is it 1 minus, the second is it 1 minus v prime?
Oh, sorry, thank you. My apologies, 1 plus. Thank you. Let me just write it out a little bit neater. VU prime on C squared. Okay. Now remember, Louis, with this reference shift to the bloke, put the bloke in the spaceship, and then the bloke becomes the imaginary receding spaceship. Now we've got to change our directions. Well, to this bloke, everything's left. So your V is negative and your U prime is negative, and you're expecting your U to be negative. So you're expecting the answer to be negative, and the two values given are negative. So let's crack it in. And as I said on the previous page, you'll end up different maths, but they end up with the same fraction. Okay. Yo. So U prime is always the speed as measured by the object that's given V. So U prime is always given... How are those your glasses?
Yeah, they are.
Okay. Frameless. Sorry. Who was that? Brandon, were you asking the question? Sorry. How's face on the foreground? U prime is always the speed measured from the reference frame that's given V. if you need to write that down, I'll say it again. U prime is always the speed from the reference frame of that which is given v. So let's look at the black text. U prime is from the reference frame of that which was given v. That's the enterprise. So U prime is looking all the way back to discovery on the left. It was given v as measured from the stationary observer. Now let's look at the green pen. U prime is from the frame of reference, the imaginary dotted spaceship. That was given v from the enterprise. Right. And so I always say, let's shift things so that we have an imaginary spaceship firing an imaginary missile. Last example, guys, I want you for the next 2 to 3 minutes, let's look at this. I believe 3.5 times 340, 3.5 times 343, 12, call it 1200, okay? So, quick guys, I just want you to consolidate this because it is tricky. Here is a spacecraft traveling v equals 1200, so even and then it fires a missile U prime at 700, and then we want to go, what does U equal? It doesn't seem very relativistic at all, but let's try and use the relativistic equation and see what it tells us. Casio ClassPad goes nah, doesn't it? I think Casio FX82 Plus. Yeah. Or does it? Let's try. Yeah, or does it? In this case, it doesn't. Wait, plus, damn it, plus. All right, let's multiply some stuff. Now, c squared, lucky for us, it's 9 by 10 to the 16. You can just multiply both. And here, I did the maths, guys, and it's 11 zeros. So 0.00000, oh, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something. Okay? Classic mechanics. So, yeah, unfortunately, your Casio FX82 just goes, nah, that answer is 900. But it's actually 1,899.99999999999 something meters per second. But not significant to our 3 sig figs. Now, gentlemen, your homework is to complete everything in that booklet. All questions, all examples. We are starting a new topic next week. Standard model, particle physics. Please get this all done. You've got a test coming up in a couple of weeks. Got it. Was that you? Yeah. Very nice. Thank you. You can still write something down now.